6. With the introduction of this, we have the purpose, which is to observe and calculate the time of a magnet falling through an aluminum foil tube using Faraday's law. We are then going to calculate the average fall time, and our computational model got 1.158 seconds. For the key equations, we're using the Biot-Savart law, which is right here at the top, Faraday's law, and Lenz's law, which is right here in the middle, which is the change of magnetic flux, and Newton's second law, which is force times equals mass times acceleration. For the procedure of this lab, we have to make a tube out of aluminum foil, which you can see here. That's how it's made, and that's a little magnet with the dude holding it. And so we have to hold the tube vertically, and then we are supposed to drop the magnet through the tube. We are then supposed to record the times as the magnet falls through the tube and exits the tube, and we have to repeat this 3 times. We then have to calculate the average time. For our lab results, we got the mass of the magnet at 0.03679 kilograms, 0.30 meters in length of the tube. The width of the tube is 0.006 meters. The inner radius 0.028 meters. The outer radius 0.033 meters. And as I said before, the average time of it falling through was 1.34 seconds. And we got the mu of the magnet at 7.6 from our previous lab 3 or lab 4. For the code, this is the first part we have to write. At first, we have to put the length of the tube, which I got 0.30, the width of the foil, the inner radius of the tube, and that's how we got the total radius. On the second part, I have to put the mu of the magnet and the mass of the magnet here. Since the code is very long, I had to break it up into 3 parts. We got that the vector field for gravity right here was negative mass times g. Well, it's the same thing as mass of the magnet times negative 9.81, which is gravity. And we put it in the y component due to gravity being in y. And you can see 5 and 6 right here. Here's like the little code for the force on the ring. And right here in the middle picture, we got the flux, the change in flux right here from code 111, from lines 111 to 118. And for 181 right here in the third picture, we got the total force, which was the force of gravity and the force of the magnetic field right here. Or my computational model, as you can see that as the thing was falling, the velocity was going into the negatives, and for some reason it did some little weird curve right there in between the from 0.2, but then it hit a constant velocity, and then it dropped, and that's when the code ended, and that's when my magnet ended too. For the assumptions and errors, we had to assume that gravitational force and magnetic force all played a part. We also had to assume that there was no air resistance and that the bar magnet was acting like a dipole. For the errors, we know that the stopwatch accuracy was not accurate, as humans are not like the best at that. We got friction inside the tube, and while we were doing the lab, the bar magnet kept like hitting the tube, and sometimes it would get stuck. So that was actually ruining our lab, and it got kind of frustrating. And we know in real life there's air resistance. And yeah, the tube was also weirdly built. It's not a perfect like cylinder, like hollow shape. It's just weird because it's just aluminum foil. It's all crumbled and everything. What if the resistivity of the conductor were reduced as close as possible to 0? How would the dynamics of the falling magnet change? Well, the magnet would be slower due to the increase in induced current. As you know, it also has like a force, and they all like go opposite ways. And since they're opposite, and it's gonna be pushing up against the magnet, then it will basically be another force pushing it up. And so the greater the force going up, the slower it will go. As compared to the other what if, the holes or slots were cut into the tube. How would this affect the ring currents in the model? Well, I said that the magnet would fall quicker since the magnetic field would break off from all the holes, making it weaker. As you know, like I said in the first part, it's like a force basically. And if the force is skipping through holes, there's less force there. And so the less force going up means there's a greater force going down, making the magnet fall quicker down to the floor. And yeah, this was my lab, and thank you for watching.